Okay, now we're going to move on induction over trees. So first off, I just want to quickly recap induction for the other different types we've used. So we've gone through induction on natural numbers. How did that work? You prove it's true for the base case. So you have some statement P you want to prove for naturals. You want to prove for the base case P of 0 is true. Then you assume it's true for some n, prove it's true for n plus 1, and then you've proven the statement P for all natural numbers n. So that was induction over natural numbers. How is induction over lists defined? We want to prove something true. We want to prove some statement P for all lists. We prove it for the empty list, that is the base case. For the step case, we assume it's true for some list xs, and then prove for any new element x, P of x cons xs is true. So the statement's still true if you assume it's true for a list and then bolt a new element onto the front. If we have these two statements, then it's true for all lists. Induction over trees is not too much more difficult. First, we should define what a tree is. So a tree is a tree of type A is either an empty tree or a null tree, or its node, this is the constructor, with three parameters. A is something of type A, which is the element at that node, and then two subtrees, the left subtree and the right subtree. So I've got some examples here to explain the correspondence between trees and their definition in Haskell. So the null tree is just like the empty tree. There's nothing there, just a null node by itself. The tree that looks like node 3 and then two null subtrees look like this. Usually when we draw the trees, we leave the nulls out. So this is really just like the number 3 by itself. So maybe it's like, sort of equivalence. And then this tree here, so the top node, the root node is a 4. The left subtree is a 5 with nothing beneath it, node 5 null null. And the right-hand tree, this whole section here, is got a 7 at the top, and the left-hand side is null, and the right-hand side is another tree, a 9 with two nulls beneath it. And again, when we draw these things, we usually leave the nulls out for posterity's sake, not posterity's sake, brevity's sake. So we usually draw this tree like this: a 4 with a 5 and a 7 on the left and the right, and then a 9 on the right. So just have a look at this for a bit and see the correspondence between the tree written in Haskell and like the actual tree we tend to visualize. All right. So now suppose we've got a function here, and this function is called rev. It's going to reverse a tree. How's it going to do that? To reverse a null tree, you just do nothing to it. So rev t of null is null. And then when you reverse a tree with stuff in it, you leave the root node where it is, and then you swap the two children, i.e. the two subtrees, and then call rev on them too. So for example, if I were to reverse this tree here, so I leave the root node alone, and then I swap the two subtrees, so the 7-9 tree goes over here, and the 5 tree goes over here, and then I call reverse again on these guys. So reverse of 5, null, null, well, that will just end up being the same when you compute it, so the 5 will go here, the null will go here, the null will go here. And then when we reverse this tree, it's going to do the same thing, it's going to like mirror flip the children. So we have a 7, a 9, null, null, and a null here. So if you can imagine drawing a vertical line down the middle of the tree, when you call rev tree, it like mirror images the tree. And then also mirrors each thing beneath it, so that way it's a full mirror image. So that's what rev tree does. And we'd like to prove some properties about rev tree. So what we'd like to prove? We would like to prove if you reverse a tree, and then you reverse a tree again, it's the same tree afterwards. So how does induction on trees work? Well, it's a little bit similar to lists and natural numbers, but a bit more work. So we have some statement P. We prove P for the empty tree, the null tree. And we have to prove we assume for some tree T1 and some tree T2. So my step case has got now two inductive hypotheses. I assume it's true for two arbitrary trees, and then I prove it's true for a new tree that's got T1 and T2 as children for an arbitrary new element A. So I've got some tree structure here with a bunch of stuff in it. I assume it's true for T1. I assume it's true for T2. So these trees got like a bunch of stuff. And then I prove it's true for a new tree built out of T1 and T2 with an arbitrary new element A on top. So I assume it for these two subtrees, and I prove it for the big tree made out of those two little trees. So that's how the step case works. If we have these two things, then we can conclude for all trees T, P of T. So let's have a go at trying to prove rev t of some tree t is equal to t for all trees t. Okay, this is the statement we want to prove. So we have to prove the base case. And the base case is where t is the null tree. So we have to prove that rev of null is equal to null. Prove rev t null is equal to null. Okay, how are we going to do that? I'm going to take the left hand side. Rev t null. If we look at the definition of rev t, it takes a null tree and spits the null tree back out again. So this is rev t null by t1, and they apply t1 again to get null, which is equal to the right hand side. Cool. Base case is proven. P of null is proven. Now I want to assume it's true for two smaller trees. So we assume true for T1 and T2, which are two arbitrary trees. So what are we assuming? We have two inductive hypotheses. The first is that rev t T1 is equal to T1. I'm going to call this inductive hypothesis number 1. And rev t T2 is equal to T2. That's inductive hypothesis number 2. Okay? There are two inductive hypotheses. And now I want to prove for all new elements A, if I reverse the tree built out of these two subtrees, so I want to prove that the reverse of node A T1 T2 is equal to node A T1 T2. Alright, so how can we prove this statement here? Once again, we'll start from the left hand side. So I've got rev t, node A, T1, T2. What can I do with this? Let's have a look at the definition of rev. Rev leaves the root element alone, and it swaps the two subtrees. So T1 goes over to the right, and T2 goes over to the left in this case. And then you call rev t again on the two children. So that's what we've done here. I've expanded out the middle. So node A, T1, T2, rev of that becomes node A, move T2 over here, and then reverse it. Move T1 over there, and then reverse it as well. And that rules by T2. What do we do from here? Well, I've got rev of a tree, so I can use T2 once more. So I leave the elements alone. So we have node A. I then swap the children. So rev T1 comes over here. Rev T, T1. And then I call rev on it again. And then the second child comes over here, and we call rev on it. So rev T, T2. And that was again by rule T2. And what can I do now? Well, these two terms here look exactly the same as my inductive hypothesis. So now I can replace them, right? I can replace rev t T1 with T1 by inductive hypothesis 1, and rev t T2 with T2 by inductive hypothesis 2. So let's do that here. This will become node A, this transforms into T1, and this transforms into T2 by inductive hypothesis 1 and inductive hypothesis 2, which is equal to the right hand side here. There we go. So I've proven for the base case I've proven for the null tree this property holds. I've assumed it's true for two trees, and then proven for a new arbitrary element A that the statement still holds. Okay, by taking it up here, taking the left hand side of this equation and cranking it out to get the right hand side for some arbitrary A. Okay, so that means I've proven it for all trees T by our definition of tree induction here, right? It's true for the base case, it's true, and we assume for two little trees and prove it for a big tree made out of the two little trees for a new arbitrary element A. Then we have for all trees T, P of T. So, therefore, for all T, rev T, T is equal to T. And that's the proof.